Okay, so D7, Taxol, a chiral auxiliary case study. So we're gonna have to dig deeper into this drug called Taxol. So Taxol is a drug for cancer. All right, but before that, we start with the concept of chirality. So what is chirality? Now, if a carbon atom is attached to four different groups, so in this example, hydrogen, bromine, hydroxide, and fluorine, now this molecule shows chirality because it has a chiral carbon or it has a chiral center. Right here, this carbon is connected to four different groups. Okay, and molecules that have a chiral center or molecules that are said to be chiral exist in two different isomers. We call them enantiomers. Okay, Dorothy and I have learned this. Austin, review the topic on conformational and configurational isomers. All right, so for example, this molecule right here is a chiral molecule. It has one, two, three, four different groups around the carbon. So this molecule can have an enantiomer, another mirror isomer of itself, like this molecule right here. Now, although they are mirror images, they are non-superimposable. So if I put this on top of this molecule, it's not going to be exactly the same. Their shape, their configuration is going to be different. So this molecule, this enantiomer, will have a different property than this molecule right here. Okay, although they are mirror images, they will show different properties because the positions of the molecules are not exactly the same. All right. Now, let's talk about thalidomide. So, thalidomide is a chiral molecule, meaning it can exist as either this enantiomer or this enantiomer. You may remember thalidomide from our bio class. So thalidomide is a drug that was prescribed for morning sickness. It was also used as a tranquilizer. It was developed in Germany, and many people during this time were using thalidomide. However, they did not know that the enantiomer, one of the enantiomers of thalidomide, can cause um, birth defects. Okay, and we are looking at this enantiomer of the thalidomide, the S-thalidomide. When you say teratogenic, it means it can cause birth defects or malformation as the baby is being formed in the womb. Okay, so again, although these are just mirror images of each other, this enantiomer can actually cause birth defects. Okay, now drugs with chiral centers, like your thalidomide, we can synthesize it from materials that have no chiral centers. So, like this one right here, it's a drug with a chiral center right here. So, this is the chiral center. One group, another different group, and then another different group. So, this drug can be made using non-chiral materials like this one. So this is not a chiral molecule. There's only three groups around carbon. So this is also is not a chiral molecule because there's hydrogen, hydrogen, the same group around carbon, same group around carbon. Okay, so to make a chiral drug, like a drug with a chiral center, we use um, molecules with no chiral center. Okay, and normally if we do that, what we produce is a drug with a racemic mixture. Okay, I'll try to explain it using molecular models. So for example, this molecule right here. Let's see. Sorry. Where did my slide go? Okay, hold on, hold on. Okay, so this molecule right here, Wait, sorry. This molecule right here. There's a fly. So this molecule right here is this, right? So you have your um, carbon double bond right here. Now, we can add another molecule on this side to make this a chiral carbon. So if we add one more molecule, that will be different from this group, it will be different from this group, and it will be different from this group. This will now be a chiral center. Okay. Now, to add a molecule, we can break from the top base, we can break this bond and attach this group, just to be clear, here, and then attach the OH here. So we can do that, right? It's still clear. Okay. However, it can also go on the other side. So instead of CH3 here, I can put the CH3 right here and the H here. So it was like this, right? First, I showed you I can open it and I can add CH3 here and H here. But I can also do the reverse on the other side. This opens up and I can put my CH3 here and my H here. Okay? So it's either I put this here and this here, or I put it like this. So when I do that, I can have a racemic mixture, meaning and I can have molecules that look like this. Then I can have another group of molecules that is the opposite. That, that looks like this. Okay, half of the molecule will be another enantiomer. So if you make drugs with chiral centers from molecules with no chiral centers, this medicine that you make can exist as enantiomers. Okay, like the OH would be here and the CH3 would be here. And that's what you call a racemic mixture. You have two enantiomers of the molecule. Well, is that a problem? Yeah, we just talked about thalidomide. There can be enantiomers of the drug that are dangerous. Okay, so if we make our drug in this way, our medicine, our drug can have a racemic mixture. It can have two enantiomers. It can have the good enantiomer and the enantiomer that can cause disease. So that's what we want to avoid. Now, how do we avoid making a drug that contains both enantiomers? Like, or in other words, how can we make a drug with only the enantiomer that you want? Okay, so what we do for that is we use chiral auxiliaries. So what is a chiral auxiliary? A chiral auxiliary is a molecule. It's another enantiomer that you can put in a non-chiral molecule to produce one enantiomer only. Okay, so you have a molecule, you put that enantiomer, and this molecule becomes a single enantiomer, the enantiomer that you want. Now, once the reaction is complete, you can just remove the chiral auxiliary. Let me explain that with this diagram. So for example, this is your starting molecule, and you want to add a chiral auxiliary here. So this is this is a chiral molecule because the carbon is surrounded by 1, 2, 3, and then there's, see here, different groups. Okay, so we add this chiral molecule, chiral auxiliary, and adding this allows this group to only attach to this side farthest from here so that you make this enantiomer. Okay, what do I mean? So For example, you have this molecule, okay? And I can break this bond, right, to add one more group here, because there's a double bond. Now, if I put a chiral auxiliary, so like this is your chiral auxiliary, if I put it here, okay, as you can see, it 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 creates like a pressure, or like it creates a prevention of pressure. I don't like that word. So it creates a shape that allows me, that results in me adding a molecule. If I open this, I'm gonna add whatever I'm gonna add to this molecule here. I'm gonna add it here, farther from here. So this limits me from adding a molecule here, because there's a lot of electron clouds here. So I can only add a molecule farther. So I can add a molecule example. So for example, I want to add this. I can only add it here, okay, farther from this side. After I add that, we can remove the chiral auxiliary, okay? So that an enantiomer that you put, you know that the, call this, the molecule that you add only goes to this side and not this side. Now, if I didn't put this, a chiral auxiliary, I can either put this here or here. If I return it back there. If there was no chiral auxiliary, I can put it here or here, right? So my drug will have two enantiomers. But because I put the chiral auxiliary here, it limited me from adding here. So I always add here, on the back side if you may. Okay? So adding chiral auxiliary limits where you can put an additional molecule. Okay? And because of that, you produce the molecule, the enantiomer that you want. For example, this one. So this is, whenever I put this is always the enantiomer that I form. Not here, attached here. Okay? Maybe to simplify, this allows you to make the enantiomer that you want. Okay? So because you added it here, I can only add my molecule here and not on the other side here in the back. Yeah, okay, I hope that's clear enough. Now, why did we have to talk about that? Because Taxol, this drug has a lot of chiral carbons. Okay, if you look at this molecule, okay, this is Taxol. There's a lot of chiral carbons. Okay, what did we say again? If a molecule has a chiral carbon, if a molecule has a chiral center, it can have enantiomers, like mirror images of itself. Now, in this case, you have a lot of chiral carbons. So you don't just have one enantiomer. You have many enantiomers. So you can rotate the molecule here, here, here. You can have mirror images around the carbon here, 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 here. There, this molecule has about 2,000 enantiomers. Okay? And not all of those 2,000 enantiomers are beneficial as a drug. Only this enantiomer, this particular configuration, okay, this shape right here, this shape of the molecule is the useful drug, is the useful enantiomer. Now we have a problem, because how can we make this drug, considering it has so many chiral carbons? How can we make it in such a way that it becomes this form right here and not the other enantiomers? Well, the answer is we use chiral auxiliaries. Now, if we look at the diagram right here, so this is the starting ingredient to make your Taxol. So this is called 10-deacetylbaccatin or 10 DAB, 10 DAB. Now, we use this as a starting material. Then we change this side chain to this side chain. And we change this hydroxyl side chain to this side chain. Like Miss Easy, change this, change this. However, hold on. If you change this side chain right here and and put this R group, okay, this R group there, this R group, this R group will have chiral carbons. So how do you know that like the configuration is this way and not the mirror image of this? And then for this one also, how do you know it's this way and not the mirror image of it where the OH is here on the top? Or here, this is on the bottom. Okay? So how do we make it in such a way that the enantiomer becomes, it will look like this? The answer is we use chiral auxiliary. So in this case, this is the shape of our chiral auxiliary. The name of this molecule is trans-2-phenyl-cyclohexanol. Okay? It's not an easy process. In fact, there's more than 10. There's 11 steps. The more modern synthesis for Taxol has involves 50 steps. So you don't need to know the steps, but you need to know the concept. To be able to attach this R group in the correct orientation here, you use a chiral auxiliary, this molecule, trans-2-phenyl-cyclohexanol. If you don't use a chiral auxiliary, this, when you attach, when you make your R group here, it can exist in different forms, in different enantiomers, not just this enantiomer. Okay. Please ask questions if this is still not clear. I repeat, from this molecule, I need to add this R group. This R group have chiral carbons. It means it can exist in different enantiomers, in different configuration, in different mirror images. So to make sure that I form this particular configuration, I use a chiral auxiliary. Okay, so the use of a chiral auxiliary can make your the enantiomer of the Taxol that you want. Okay. All right. So Taxol, another name is paclitaxel. Okay, and we use this medicine for treating cancer, so mainly breast, ovarian, or lung cancer. We give it in the blood, and it's part of the chemotherapy to treat cancer. And what it does is, so you need to know this concept, it prevents cell division. Now, uncontrollable cell division is cancer. So this drug prevents cell division. How does it prevent cell division? They say Taxol binds to microtubules. So microtubules are like filaments that form in your cell, so it can pull your cell apart and divide it into two. So Taxol binds to those microtubules. Therefore, if they bind to the microtubules, it prevents the filaments from forming and dividing the cell. Okay, that's how Taxol works. And we discovered this drug from the bark of a Pacific yew tree. So this bark of the tree produces that active ingredient Taxol. However, to treat just one patient, they say you will have to use a big part of this tree. So you take the bark from more than one tree just to treat one patient. So instead of getting it from the tree, we do the semi-synthetic process. What is the semi-synthetic process? It's the one that we just learned. So we get this 10 DAB and then we just put an R group. So this one we can collect from the leaves of the tree. Okay, so the tree has so many leaves, so we just get it from the leaves. And then we transform the molecule from 10 diacetylbaxetine into Taxol. Okay. Don't forget we use chiral auxiliaries for that. All right. Um, okay. So how do we know? Like after, so you get the 10 dab, you mix a chiral auxiliary. How do you know that you only have one enantiomer Taxol in the solution? Okay. What we can do is we can use a polarimeter. What is a polarimeter? So a polarimeter is where you have a light source, and this light source, the photons of the light can go in different directions. So you put a polarizing filter. If you put a polarizing filter, you arrange these movement of the photons into one direction only, like a wave. Okay, and um, if inside this tube there are two enantiomers, the first enantiomer can rotate this wave clockwise. So imagine clockwise. And then the other enantiomer can rotate the wave of the light counterclockwise. Okay? So if you have two enantiomers inside this tube, there's two enantiomers. One will rotate your wave clockwise, the other one will rotate it counterclockwise. So clockwise and counterclockwise, they cancel each other. So in other words, they cannot, they cannot bend the light. So there's no, it does not polarize the light. What? But if you only have one enantiomer, then it can bend the light. Okay, it can rotate the light. You can measure the light rotation, and specific enantiomers have a specific angle of rotating the light. If if there's only one enantiomer present there, it should rotate the light as it goes out of this tube. Okay? So if there's two enantiomers, light will not be rotated, light will not be bent. In other words, you have several enantiomers or at least two enantiomers inside your sample. But if it's able to rotate the light in one direction, then it means you only have one enantiomer present here in your sample. And if that's the case, then you know that your sample is pure and you have that one enantiomer that you want. Okay, the other enantiomer is absent. All right. I think this is the last slide. Yes, it is.